Right, good evening, everyone. So welcome to this very well-attended meeting. I'm setting some sort of record here. Particularly welcome to all those kind of new people who have not been to a ROUGOL meeting before or not in a long time. As you may know, we normally hold real physical meetings in a pub near Waterloo. But since we've gone online, it's been at least allowed people from around the world to drop in. Right. Now it was 11 years ago exactly to the day that Sophie visited us in person. So much has happened in the microprocessor world since then. So Sophie's now going to tell us about what's happened and maybe what the future might be as well.
So this is a talk about the future of microprocessors, which means we're going to spend a lot of time looking at the history of microprocessors. Yeah, why doesn't that do page forward? So I think we're all distinctly aware that we now rely on microprocessors, broadband communications, video compression systems, all things that I've worked on in the pandemic. But generally speaking, even without a pandemic, the world relies on all of this technology. Specifically, microprocessors are everywhere. Over the 40 years since it was introduced, microprocessors have become approximately 10,000 times faster, but billions of times more common. So we'll look at how we got here, and we'll try and look at what the future might look like. There'll be two laws, actual laws, and some graphs, and an equation, I think. The first law is kind of obvious. If anybody who talks about microprocessors has to mention Gordon Moore, I have to sign an affidavit that I would. Microprocessors are made out of transistors, so the evolution of microprocessors follows Moore's law mostly. So although it's called Moore's law, it isn't actually a law. It's an empirical observation that the number of transistors on a piece of silicon doubles every 2 years. Though when he first phrased the law, it was doubles every year. And currently, if you're looking in detail at the top right of the diagram, it's not quite doubling every 2 years at the moment. But anyway, it was taken, the law itself was taken that the fulfilling of it would be the driving force for the development of new silicon manufacturing. And we've had two governing bodies during all this time. The first one was the ITRS, the International Technology Roadmap for Semiconductors. That's now been replaced by a similar body, the International Roadmap for Devices and Systems, IRDS. They found that just making it work for the semiconductor itself wasn't good enough. You needed to consider the system interface stuff as well and make sure all of that worked. And we'll see towards the end of this presentation the results of some of that thinking. Of course, you don't have to be using all the transistors. There are some notable low points on the bottom side of the upwards curve. They happen to be ARM microprocessors, which didn't use as many transistors as they could have done at the time, but that was deliberate to have them be cheap. Or, well, I don't mean cheap as in cheap, I mean cheap as in inexpensive. So I think most of you will have heard of Moore's law, and the numbers are astonishing, but what does it actually mean in practice? So on the wall behind me is a plot of ARM1 in the 3-micron process it was designed in. I mean, not to actual size, obviously, but to the same scale in my hand is a plot of an ARM Cortex M0 Plus in a modern, with air quotes, 20 nanometer process, and it's the small black dot. It's 70,000 times smaller than the original. Which basically means that it got many, many more times than 70,000 times cheaper. Those of you who are familiar with the ARM processor development will understand that this is quite significant because ARM1 was designed to be cheap, to be put into consumer class computers. So having it become 70,000 times cheaper is an obvious factor in there being billions or hundreds of billions of ARM microprocessors in the world today. They had to be as cheap as washers before you get a lot of them. You don't get as many when they cost $5. So let's look at some microprocessors that have historical relevance, and we'll see what Moore's law means to us as users of these things. So the 6502, the microprocessor in the BBC Micro, had 4,000 transistors when it was implemented by MOS technology back in 1975. For this slide, I've done something a little bit unusual. On the left-hand side of the slide is a die photograph of the 6502. You'll see a lot of die photographs in this presentation. It's important to understand that although they're nice, pretty colors, the actual die is quite dull and boring. If you opened a 6502 at the time, you'd have seen a greyish slug of stuff, which you'd dimly be able to see was a bit rough and patterned. The bright yellows, blues, reds, and greens in this picture are produced by shining strong white light sources at the die at different angles. So we get different colors where light refracts through the silicon or bounces off metal grids. That green bit, it has got a metal grid on it, and the light bouncing off that has done lots of diffracting and interfering with itself to get that. Other metal grids up the right-hand side give you that red color. On the right-hand side of this thing, there's the circuit diagram of the 6502 displayed as transistors. It's not that I expect you to read and understand the circuit diagram of the 6502. It's there simply for the purposes of reminding us it really is transistors. Microprocessors are built out of them. Amusingly, the circuit diagram has been topologically distorted to match the final layout. So that big green thing that I've mentioned before corresponds to the black greyish thing at the bottom of the circuit diagram, which is the 6502's main PLA decoder. And you can see that there's a correlation with big black lines and little other lines on the right-hand side and left-hand sides. It's just to remind you, normally we never look at the transistors in a processor, but this one, obviously, when it was designed by people who had to think about all the transistors. The 6502 was designed and laid out entirely by hand in a bungalow in Phoenix, Arizona, by some electronic engineers who were sitting with big drawing boards and sticking strips of tape to make a rubylith mask. So they'd have a big transparency, and they'd stick bits of tape where they wanted a piece of metal or a piece of polysilicon for each mask layer. So this is designed entirely by hand and laid out by hand. In Acorn, we did much the same thing. The SURPROC and VIDPROC and the tube were all designed and laid out semi by hand, but using computers as our drawing boards rather than actual big drawing boards. Anyway, we don't usually look at the transistors, we usually look at a block diagram. So the block diagram on the right is very typical of the breed. You get a sequence of boxes, they're collected by big lines, which in this case represent 8-bit buses, or little lines, which represent single-bit signals. We won't, for this talk, go deeply into what's going on to actually make instructions work. I can talk through if anybody wants their minds blown, but there's no real point generally. So when the 6502 was designed, it was designed using really quite big things. A process was used which corresponds to about a 6 micron smallest feature size. So 21 square millimeters had those 4,000 transistors in it. So that's what? It's 1,000 transistors per square millimeter. Is it? No. No, that's useless piece of maths. Somebody do the division and tell me. So 4,000 transistors isn't really very many. It's enough to implement some 8-bit operations, instruction decode, 8-bit add, but there's not enough transistors to design a multiplier at all. So you don't get a multiplier. It's not enough transistors to store a lot of information. So you only get a program counter of 16 bits, an A, X, and Y register of 8-bit. And it's not enough for a really fast implementation. Well, it's not enough twice. At 6 microns, the transistors were quite slow. And there's not enough for advanced techniques of putting the machine together to make it go faster. So in the Apple II, the 6502 was run at 1 megahertz. We ran it at 2 megahertz in the BBC Micro. At 2 megahertz, an 8-bit operation such as add with carry 9 gets the immediate number 9, adds it to the accumulator, puts the result back in the accumulator. That took 2 clock cycles or 1 microsecond. If you imagine trying to use the 6502, you're probably aware that some very talented programmers did things that the people at Acorn could not believe. We could not believe it when we saw Revs, the game. We couldn't believe the first flight simulators, and we multiply couldn't believe that Braben and Bell had done Elite. It was quite fun having these people come along and blow our minds. If you're doing simple programming, you might have a typical bit which we'll use to compare microprocessors as we go forwards. So we'll just say we've got 3 integers A, B, and C that are 32 bits in size, and we'd like to add A to B to make C. On the 6502, well, that's quite a long sequence of instructions. We can only operate at 8 bits at a time. So to do a 32-bit add, we need to do it 4 times over. And we don't have any storage. So we can't save temporary values. We've got to load each one, add, and store again. But we can at least add the value as it comes in from memory. So we can load from address A, add address B, and store in address C, and then repeat. So the best case for this sequence is 26 cycles. And that's typically what, say, the BBC Basic interpreter on the 6502 did to add 2 integers together. So that's a very real thing. So one of our metrics going forward was, people could startle us on the 6502. They could do real Wizzo programs. When we started designing ARM, we wanted them to be able to do the same sorts of Wizzo things, but much more easily, writing high-level languages at the speed that a genius, Braden Bell type genius, could write on the 6502. So why could we design an ARM? Well, we've got more transistors to play with. You don't have to wait many years before you can have a lot more transistors. So going up from 4,000 transistors on quite a big die for the time to 25,000 transistors in 1985 does allow you to do lots of things. So on the left is Steve Ferber's original pencil sketch of the floor plan of ARM1, and on the right is the obligatory die shot without quite as many jazzy colors. you can immediately see there's something different between that picture and the 6502 picture. Things are much more regular and regimented. And there are some very big features that are clear to see, in particular, the very big block of registers. And the equivalent of that green block seems to have gone missing. There is a block on the right-hand side, quite a nice silvery coloured block, that is the instruction decoder, but it's now become relatively very much smaller than it was on the 6502. So, with more transistors, you get to spend more of them doing interesting things while devoting a smaller percentage, but maybe the same number of transistors anyway, to the general housekeeping operations that make your processor work. So if we move across to the block diagram, this is the picture in one of our early presentations of ARM. And we look down and say, right, it's a 3 micron smallish feature size machine. So we've got faster transistors, but critically, we've got a lot more of them. We can spend transistors to make the machine faster. We can pipeline it. And so not only can we have 32-bit operations, but the full execution of a 32-bit operation takes one elapsed cycle, 125 nanoseconds, when it was released in, whenever it was, 1987. We've had them in-house from 1985 onwards. So we get 32-bit operations, we get lots of registers inside the processor to store things, and we get enough transistors to burn to make it at least semi-pipelined so that it can continuously do instructions back-to-back overlapped. So pipelining means that that example add operation gets to read the values out of the register file in the first cycle, do the add. Well, actually, I've skipped many things, haven't I? You've got to fetch the instruction, decode it, read the register file entries, do the add, and write the result back. So we chose to do the add and write the result back in one cycle, and fetch in another cycle, and decode and read it in a cycle. So all of those things then are executed in a pipeline to make the machine go quicker. The big impact of the machine is when we look at our piece of C and we get a much simpler realization of what you can do. And part of that is that we made the machine simpler. You can no longer execute on data as it comes in from memory. You can only execute on it as it's sitting in a register, but there are lots more registers. So there's a big chance to reuse that data that you brought in the first place. So C equals A plus B, load A, load B, add the two things together, store it as C. Yay! C compiler man, very happy. So few instructions, easier to write. Clock runs faster because the machine is pipelined. And that all combines into we run the clock 4 times faster, and we run the sequence itself in 3 times fewer cycles. So ARM is 12 times faster at doing this than the 6502. It's actually faster than that for many more complicated things. So that thus far, fairly obvious. We sort of know what happens next. If you're given more transistors, you can make more complicated ARMs, as we see the world is still doing today. But I'd like to look a little bit at the effect that more transistors have on instruction design. So we'll look at Firepath. So this uses 6 million transistors when it was designed in 2003. Firepath is the processor that I built after ARM. It's the processor that is running the DSL, VDSL, G.fast broadband line that comes to my house, and probably yours. This Zoom call is brought to you by a broadband infrastructure that is essentially going to contain ARM processors and Broadcom chips at virtually every node, and those green cabinets on the curb bring in VDSL or G.fast to your house, have my chips in them, or the exchangers near to you that have ADSL or VDSL chips in them, they're my chips too. So Firepath is a processor built for the purpose of doing that. Looking at the picture, you can see, well, the nice structures that we saw on the ARM picture have gone away. 6 million transistors is a bit much to display a picture of. There's some features, those vertical yellow bars at the right-hand side, which are its register file. So that's a large amount of the silicon dedicated to the register file. But then there's two symmetrical, about the middle pipelines of GUI stuff. And that reflects another difference in how this chip was designed compared with ARM. On ARM, all the transistors were laid out on a computer assisted by computer programs, but still plotted by hand. On Firepath, silicon compiler, synthesizer, made those transistors only very loosely directed by hand to instruct it about its placement. So, as we'll see when we get even more modern pictures of processors, any notion of structure seems to have gone away. We only design computers on computers, and the computers aren't as artistic as humans were, but humans couldn't lay out a 6 million transistor Firepath, let alone a billion transistor processor nowadays. So what you get for 6 million transistors? Well, we can burn a lot of transistors to make it go faster. We're in a 0.13 micron process, so the transistors do go quite a bit faster anyway, but we can go to a 9-stage deep pipeline on this machine to make it run at 330 megahertz back in 2003. We also get the ability to do many more operations per cycle. Firepath will do 4 64-bit operations per cycle, which you can regard as 32 8-bit operations. And somewhat unusually, when you write instructions for Firepath, you are able to write for all the execution units at once. So a typical instruction on Firepath is that line add word R0, R1, R2, R3, R4, R5, colon, LDL2, R6, R7, R8. And that's a single instruction for the processor that just happens to use multiple operation parts of the processor. So Firepath has 2 load store units that the LDL2 touches, and the add word instruction touches the ALUs of the Firepath, all in one instruction that the program can write. So you're doing 4 lots of 64-bit operations. It still only takes a single clock cycle pipeline to do that. Firepath is quite small. It was 7 square millimeters at the time, which, if you've been remembering the 20-odd square millimeter numbers from before, means that we've got a large number of transistors into a much smaller space than we had before, but then we are using a 0.13 micron process. if we look at our piece of C, then it's somewhat disappointing. Sure, you can do 2 loads in a single cycle, and then an add and then a store. And sure, Firepath is doing multiple adds at the same time. So we can do 2 32-bit parallel adds with that single add W. Indeed, we could have done more adds. So for C, Firepath may have an instruction set that the C compiler can't really access very well. If you look at the bottom, that's what Firepath's designed to do. Mul2W, R4, R5, R0, R1, R2, R3, LDL2, R0, R1. So it's loading 4 32-bit integers and multiplies 4 32-bit integer pairs together, and that still only takes 1 cycle. So we burned a lot of transistors in Firepath to be able to have that sort of fun. But you have to realize that having that sort of fun does mean that you end up with something that isn't generally useful in your typical C programming environment. But of course, if you want to do signal processing, then that's just lovely. So there is a general feeling that we have designed as complicated instructions as we want. Most processors nowadays have enough transistors that they can have all manner of floating point, integer multiplies, divides, transcendentals, whatever, implemented in their instruction sets natively. That's not the hard bit. The hard bit is getting the data and moving it around and doing so quickly. So really, what do you do when you're given more transistors? And the answer is that you tend to make multiple microprocessors. So this is the 2003 Central Office ADSL 2+ chip that Firepath was in. And you can see that there are 2 Firepaths horizontally affected about the middle, and then there's lots of dense blocks of colored memory and very little random logic. The Central Office DSL modem is running Firepath software without much help. And this is a picture that you get quite familiar with. Structured logic of processors with lots of memory on chip. And if Moore's law's handle is cranked again and you get given more transistors, then you put down more microprocessors. So this is the 2006 Firepath Central Office chip with 4 Firepaths on it, doing slightly more than 4 times as much work as the preceding chip. But there's a problem. We can keep giving you more microprocessors, but it keeps being less useful. So this one really is a law. It's got a graph and an equation and everything. It really is a law. So the speed up of multiple processors is limited by the sequential part of the program. So speed up for n processors is given by the equation. I've plotted some of the answers on the graph. If we look at the green line, that's an insanely parallel program. It's 95% parallel and only 5% of it is scalar. As we increase the number of processors horizontally, then the speed up factor goes from 1, it rises and rises quite rapidly, and you're thinking, oh good, these multiprocessors are really useful, but you keep adding more processors and it stops. And no matter how many processors you add, you never get more than a speed up of 20. Amdahl's law is quite vicious. And that's a program, 95% parallel is not any program that you'd run. That's sort of ray tracing levels of parallelism. The purple line is 90% parallelism, also quite rare. The speed up stops at 10. The red line, 75% parallel. With care, a good web browser could be written to be about 75% parallel. The speed up stops at 4. with care, a compiler could be written to be about 50% parallel. The speed up stops at 2. Amdahl's law is a real serious problem for the evolution of microprocessors if we're simply going to rely on increasing the number of processors that we sell you. Nevertheless, the industry can and will continue to make hardware that has ever-increasing amounts of parallel computation ability, and we can do it with both multiprocessors and adding SIMD data types and vectors. But traditional scalar computation will not increase very much. Indeed, it hasn't increased very much since about 2006, though it has got considerably more power efficient. And what's immediately obvious, scalar programming languages are a really poor fit to the parallel hardware. And furthermore, we don't have automatic compilation of scalar to parallel that works for all problem types. We do have conversion for some limited problem domains, but not for most. So if you're going to use the parallel hardware, you either have to write scalar programs which you try and coordinate multiple threads of or multiple copies of on multiple processors yourself, for which there are very poor tools that let you down frequently, or you need to move programming languages to explicitly parallel languages, in which case there are very few programmers that know how to use them, or you need some smart person needs to go out and write some new software. We need a new way of doing that because it's a real problem. The other real problem, more transistors just aren't as useful in increasing the performance. So we've been doing this long enough to have different epochs in the life of microprocessors. So back in the pre-RISC days, starting in 1978, VAX 11780 era, we had improvement every year. You could go from your VAX 11780 and get a new one, get a microvax later on. And they were getting a bit faster, about 25% per year. And that was all basically transistor scaling. The transistors got smaller, they got faster, capacitive effects went down a bit, and you were stuck. Then you get the beginning of RISC chips. So suddenly with RISC chips, things are more obvious. Internal barriers to scaling fall away, and there's quite an arms race. You see a 52% per year performance improvement with the various RISC chips. This is an American slide, so arms aren't mentioned. But after a while, that gets really hard. By the time you get to gigahertz processors, many other system effects are beginning to hurt. Particularly what happens is that you keep stalling on bringing values in that aren't in your cache hierarchy. So starting at the end of that 52% a year, we start moving to more latency tolerant architectures. Out of order processing is a way to cover up the cache miss latency by doing something else at the time while you're waiting. It's quite a successful technique. It's used in most things, but it doesn't give you great improvements. So we're back to a slightly slower rate of increase. And then it gets even harder, really. You can, out of order processors have got to as it were, fever pitch, and it's proving very difficult to improve them. We're still able to do multi-core, but Amdahl's law limits the speed up of that. So then we entered a period of 12% per year growth limited by Amdahl's law. And now we've entered a period of, it's really hard to make the transistors faster and give you more of them anyway. So what we might think of the end of easy Moore's law, we're still making faster, better transistors that are smaller. It's just costing a real large amount of money. Anecdotally, I bought a laptop in 2006 with an Intel Meron processor in it, which ran at 2 gigahertz. And that laptop lasted a long time. I gave it away to help with the pandemic to children in schools, and it was still capable of doing useful work. It used quite a lot of power for its speed. It ran at 2 gigahertz. But it's very hard to build machines that are more than twice as fast as that laptop. Very, very hard. Now, there was another problem all the time. Every time we put down more transistors, we did so because we got given them, as it were. Transistors got more power efficient as we made them smaller, but we used so many of them in such a small space that our power density goes up. This is Intel chips. So Intel started off with the i386, making a nice out-of-order processor, nice in-order processor, improved it with the 486, made some better 32-bit data paths and processing, used a lot more transistors, got a bit more power hungry. Then they came along with Pentium, the first out-of-order Intel microprocessor, Pentium Pro. Oh, now they've hit hot plate levels of heat density, power density. That means you can now fry an egg on your Pentium Pro processor. Have to be a small egg, quail's egg or something, but you can. Intel didn't really think of this as a problem, so they cracked on, made Pentium 2 and Pentium 3. Then their graph starts to go sideways a bit. It's really getting too hot. Pentium 4, the so-called Nehalem processor, nearly, but not quite, and kudos to Intel for trying, got to nuclear reactor levels of heat. Does leave rocket nozzle a little bit far away. They took the lesson from Nehalem. Nehalem was a dreadful lesson to them that you couldn't keep using more power. You had to do something. That something was to go back to the drawing board and start again. And on the slide, it says Core 2D and Core i7. Intel had to redesign entirely how their processor worked, following the designs of their Israeli group who specialized in a low power laptop processor. And that processor has become the Intel Core processors that we know today, abandoning completely the Pentium 3 and Pentium 4 Nehalem microarchitecture that they'd spent so much time developing and pushing up. And power still constrains us. So as we go forward, increasing amounts of the silicon must be left unpowered, even assuming that we make better and better transistors. For a while, the 28 and 20 nanometer generations, we made very bad transistors. They were leaky, and that added to our heat problems. When we went to multi-gate FinFETs and the future, which will be another slide, of transistors, then they became a bit more efficient and we could use more of them. But even so, we're still carrying more and more into the same space. Now, this works. You can have your iPad, you can have your watch, your phone, your laptop, etc. It works. We just turn off most of the silicon that you've bought, or we clock speed limit it. And as we go forward, we'll sell you silicon die with more and more transistors on it. You just won't be able to turn them all on at the same time. Next year, I expect to see people selling chips with the 125 watt sort of desktop computer power limit, where half the die will have to be turned off for the other half of the die to be turned on, or you'll have to run it half as fast, which is the equivalent. Intel have been playing very fast and loose again. So they sell you a processor which they call 100 watts, and you look at it, and its peak power usage is something round about 250 watts. It gets hot very quickly. It throttles its clocks back to get cooler again, and so on. In laptops, Intel like to sell you a processor which they say is a U suffix on it, which is a 15 watt power limit. Those things go up to 28, 30 watts, get very hot, make your laptop's fans go on, throttle itself back, get cool again, then go fast again. Or it goes fast, but only by running one of the cores fast, and the other cores have to be not running at all. Going forwards, we stack things in 3 dimensions, we stack memories over processors. So going forwards, hotspots can only get worse. We keep increasing the power density to make devices small or to limit electrical distance problems. So we keep concentrating all the power into a smaller and smaller space. So you're just going to have to get used to buying machines where they don't reach their theoretical capabilities due to power limits, or they're turned off most of the time. As I said briefly a moment ago, there's no immediate physical limit to scaling. We can go a long way forward. So lots of chips are being produced on 28, a few on 20. Intel, Huawei, Qualcomm have 10 nanometer chips in production. You'll note there's a little star. We'll come back to that. AMD and Apple have 7 in production. Huawei, Samsung also have a little at 7. Everybody is claiming that they have 5s, 4s, and 3s in development. But these things are expensive. The devices that we produce nowadays with 10 or 7 or 5 in them are costing more. If you remember our past, not only did you get a new, shinier computer each year, it was cheaper than the computer that it was replacing. And that's not true anymore. The new shiny things are still better. They usually give you more compute and other advantages such as lower power, more portability, but they're costing more than the devices they replace. And this comes right back to, it's really hard to do this stuff. 10 nanometer, 7 nanometer, the transistors themselves, they're much smaller. They use a lower amount of silicon, but the cost of producing the die is higher. The cost per transistor is higher, and development and mass costs are far higher. So in the past, Moore's law was a tide that lifted all the boats. But now, although we can make better, faster, cheaper, smaller transistors, they're not cheaper transistors anymore. So only a few things will be worth the greater expense of really small process geometries. For a lot of people, you'll see them stop at 28 or maybe 16 if they can afford it. And you'll see startups produce their first chips on 28 or 16 just to prove the concept, and then get their backers to fund the money for making it smaller. It's really expensive stuff. Now, those star marks on the slides. So we moved over time from planar transistors, where we slapped down some bits of polysilicon, N-type and P-type, and put a metal gate across the two of them as they butted together, and we got a field effect transistor. When the industry moved from FinFET transistors, starting with Intel, it moved from 28 nanometer to make a new process with a FinFET transistor. A FinFET transistor, the fin bit is a vertical fin, like a shark's fin, sticking up off the silicon. And that's the metal gate. And we wrap the metal gate round the fin. Yeah, it's the isolation there. So a flat transistor became 3D, but we didn't change the process geometry. The smallest pieces of metal we could build were the same, the smallest pieces of polysilicon, insulator, etc., that we could put down were all the same. It's just that the linear dimensions of a transistor sort of shrank in a bit because some of it projected up in 3D out of the silicon. So the industry made up a new name for the process as if we still used flat transistors. So when Intel made the 22 nanometer process that Haswell was made on, it was made with a 28 nanometer line, and they just called it 22 nanometer. 16 nanometer FinFETs or 14 nanometer FinFETs, if you're Intel, are made on a 20 nanometer flat process line. And after this, although we've been using 12, 10, 8, 7, 6, 5, 4, and 3 disclosures have all been made, they're all made on pretty much the same process, and it's different tweaks to the FinFET geometry and how things are aligned and basically marketing lies. Intel chose to lie differently to everybody else. TSMC and Samsung were very aggressive in their making up of new node names. Intel a bit less aggressive, but it does mean that there's no real equivalent between names. They're just marketing slogans, as it were. Back in the days of 130 nanometer or 65 or 28, there were real things that in the transistor that you could measure and say, yes, we really are doing it. It's really like that. Now, I mean, a 60 nanometer FinFET is probably 70 nanometers wide. A 10 nanometer one might still be a similar width, just a different in another dimension or different in the way it can be packed together. Marketing rules. So I talked about it being hard. In order to maintain Moore's law, it takes approximately 18 times as many scientists, researchers, etc., as it did in the 1970s. Which, of course, if you look at it the other way up, that means each researcher's output is 18 times less effective in terms of generating economic value than it was several decades ago. You can actually work this out on an annual basis. Research productivity is declining at a rate of about 6.8% per year in the semiconductor industry. You could say we're running out of ideas. I mean, it's just getting really hard and hence economically expensive to do this stuff. At the same time, actually, we are seeing a reduction in the number of places things are done. We're down to 1s and 2s for certain types of basic research. At this point, we start wanting to look at the future. So it's always a good time to remind people. Predictions are hard to make, especially about the future. In April 2002, the head of Intel, who should have known better, predicted that we'd have 30 gigahertz, 10 billion transistor chips by 2010. And we've seen some of the reasons why they massively missed their goals. So I'm no better than that. I'm probably worse. So what we say now about the future could easily be wrong. On the other hand, I have been presenting variations of this slide set for about the last 9 or 10 years, and most of the predictions have held so far. So it will sound for a while like I've got it in for Intel. They were the world's leading fab and leading manufacturer of microprocessors. So it's important to look at their predictions and see just what went wrong. So back in 2010, Intel held their investor meeting and stood up and told their investor meeting that, yeah, it's looking really good for us. We're doing really well. I think they were on Haswell's successors, Broadwell. I think they were just about. What does this look like? Yeah, they had Broadwell in development in-house at the time, and Haswell was just about to be released to manufacture. So they stood up in front of their investors and said, "This is looking really great. We've got this amazing 22 nanometer FinFET process that we'll start manufacturing next year with the Haswell processor. And looking forward, we've got a shrink to 15, a shrink to 11, a shrink to 8 by 2017. We've got all these methods of improving things, which I won't bother reading out. And stick with us, kid, we can't go wrong." This is what actually happened. So Haswell actually, even though it was really close, didn't go out until 2012. They didn't make the transition from 22 to 14 until 2015, 2 years later than they said. They didn't make the transition from 14 to 10 until 2014, 4 years later than they said. They still haven't really made the transition to 7 nanometer. For those who are Intel shy, Intel have this thing called SuperFin FETs, and it's a 10 nanometer process again. So back in 2019, probably most people will have missed it. They introduced a single chip in 10. It wasn't a success. They had to go back and redesign 10. So they are now launching Rocket Lake and Ice Lake chips are on SuperFin 10 nanometer plus. So that's 2021, and they're still on 10. Things haven't gone according to plan. And I don't mean to be cruel to Intel scientists and researchers, etc. I think Pat Gelsinger is going to be cruel enough. It's hard. So there are fewer people on leading nodes. When we made Firepath, there were 22 companies that we could have gone to have it fabricated in 130. When we transitioned to 16 nanometers, there were 4 companies left. And now at 10 nanometers, there are 3 companies left. And it's just getting really expensive to build a fab, to develop the process. How expensive, you may ask? It's very difficult to tell from the outside. TSMC, one of the big foundries, are spending roughly $30 billion a year on doing fab investment, fab implementation, with a little bit of process development. Every year, well, 2020 was a bit special, but in 2020, about $75 billion was spent on the machines that go into fabs. So that sort of discounts the building of the fab and the staff in it and all those sorts of problems. Just the machines that go in worldwide, $75 billion. Which is quite an expensive game. The semiconductor market itself is about $400 billion. So that's a substantial portion of the revenue to spend on just implementing fabs. This isn't a brilliant business to be in unless you're Intel or TSMC. This is essentially where we've got to. So Intel, Samsung, TSMC are the top players. Global Foundries, well, essentially they dropped out at 12 nanometer and said we're not going further forward. SMIC and UMC have said they're going further forward, but the time at which they will go further forward is still in the future. I'm fairly skeptical that they'll meet their 8 to 10 nanometer FinFET in SMIC. So if we look at the top three, Intel I've already mentioned, had 14 in 2015, 14 plus in 2016, 14 plus plus in 2017, 2018, a sort of unsuccessful 10 nanometer in 2019, a more successful one in 2020, and superfin now, and there'll be a tweak to superfin, and then they say they'll go for 7 nanometer. Samsung, considerably more successful, but they're a fairly low volume supplier. So they're substantially ahead of Intel, even if you account for, as it were, grade inflation in their naming conventions. And TSMC are currently the most successful. Taiwan Semiconductor Manufacturing Corp got to 7 nanometer before everybody else, even if it was a bit optimistic in its naming. They built a 5 before everybody else. They're in production at volume on 5. Again, even though the naming is somewhat optimistic, and I think we can trust them that later this year there'll be 4 as a follow-up to the 5 process, and sometime at the end of next year there'll be a 3. And it looks extremely likely that the 3 will beat Intel 7, even if Intel can keep it on time. At the moment, in microprocessors, TSMC are fabbing both Apple's M1 and all the AMD Zen 3 cores. So they are on more successful processors for their processors, and are certainly giving Intel what might be termed as a bit of a kicking. It's difficult to compare directly. This is the best I've been able to do. Transistors per square millimeter isn't a very reliable metric, but it helps give some idea of how much grade inflation there has been. I mean, other things that matter are how close can you put the tracks, how do you put vias through them, what's the power, what are your layout rules, how restrictive are they, etc. So back in 2017, where you had TSMC on 10, Samsung on 10, and Intel on 14++, Samsung and TSMC had a similar number of transistors, and it was a significant, but might call it slight gain. 2018, TSMC are beginning to be able to put twice as many transistors as Intel. 2019, if we trusted Intel with their first 10, then Intel got back to parity, but Intel had production problems with that, whereas TSMC had no real production problems at all with N6. And TSMC evolved to the 5 nanometer process, and again have a very substantial advantage in terms of number of transistors. 170 million transistors per square millimeter. And it must be said at this stage that Samsung are actually trailing TSMC by what looks like an increasing margin. TSMC are being quite aggressive. Let's just switch to looking at the machines that make transistors. So here's that chart of microprocessors again, and I've cut out and stuck on the chart pictures of lithography machines. All microprocessors and transistors are made using lithography, essentially a sequence of masks to make your semiconductors, where you project through the mask to make a single layer, then change masks and make another layer, etc. So lithography machines and the growth of lithography machines are central to the story. So back in the 1980s, lithography machines were pretty much like big office photocopiers. They even look a bit like them. They're a little bit bigger than a photocopier. As the wavelength of light moves down, the machines get bigger. And now we're on extreme ultraviolet. We actually had a lithography failure. So from about 2000 to roughly now, we've been running on deep ultraviolet lithography. As we make the wavelength of light shorter and shorter, we can print finer and finer details. So that's kind of obvious. So we've been building all these chips with 193 nanometer deep ultraviolet light. You'll notice 193 nanometer is a distressingly larger number than, say, the 70 nanometers that I referred to as a transistor size. It's how far a transistor is across. How do you print something smaller than the wavelength of light that you're using? Well, the answer is you use multiple mask layers, multiple exposures, and a bit of computational lithography. You pre-distort the mask to account for diffraction effects, which is all quite expensive and annoying. So on 28, you could get away with 30, 40, 50 masks because you were only using single exposure lithography from the diagram on the left. So with a single exposure, you could pretty reliably build 28. You could build a 22 FinFET and even a 16 FinFET. But then you have to start using double exposures. This slide refers to it as self-aligned double patterning, two different masks that align to themselves to produce a smaller feature, and was currently using self-aligned quad patterning. So that's very annoying, because when you're into hundreds of masks, that's one of the reasons transistors have stopped costing less. So the industry has wanted for a long time to use a smaller wavelength of light to move from 193 nanometers to 13.5 nanometer, extreme ultraviolet light. And that's turned out to be rather hard. The picture on the right is a diagram of an EUV machine. The particle beam weapon from space. This is the Star Trek stroke Star Wars, whichever franchise you prefer, laser beam weapon. How do you make extreme ultraviolet light? Well, the answer is you make droplets of molten tin in a vacuum. So you have a source of tin, you melt it, little droplets fall out in the vacuum, and you get your megawatt laser, which you're packing under the foundry floor, and you vaporize your droplet of tin. If you've seen the Star Wars or Star Trek movies, you know what happens when you fire a phaser at something. It explodes violently and sparks go everywhere. the violent explosion of your piece of tin produces lots of colors of light, some of which is extreme ultraviolet. So the thing labeled vessel is a set of baffles to stop the wavelength of light that you don't want and let out the wavelengths of light that you do at the end of the machine. And so you started with a megawatt laser and you end up with about 200 watts per square centimeter of EUV to feed the rest of it. So the sort of theoretical diagram is dwarfed by a picture of the actual machine with a human next to it. And remember, there's a CO2 laser underneath the floor. So this is the ASML TwinScan NXE 3400, now being superseded by the 3400B, that is a EUV light source. And so the supply of these machines is one of the reasons why it's been so hard to ramp up production of advanced 5 nanometer and below processors. Intel has got to 10 nanometer without using EUV and will insert EUV into its flow at 7. TSMC also got to its 10s and 7s without EUV, but inserted at 7. So 5 has some EUV layers. They're not all EUV, just a few of the critical layers. And nobody's entirely sure what Samsung is doing with the EUV machines that it has purchased. So conclusions from all this stuff. And this will be a good place for me to have a short break and come back for the next bit. So we will have the ability to have as many microprocessors in your chips as you like, heterogeneous microprocessors, graphics processors, other types of processors, single processors, lots of work for people who design processors and system on chip, even more work for software people, but that thing, performance is related to parallel special purpose programs only. So users of computers will have to adjust their expectations. You've lived through a lifetime of computers getting ludicrously fast at executing scalar C, and that's just not going to happen again. And you will all have noticed that computers, shiny toys, etc., cost more each iteration, and that costs are going to continue rising. Were there any questions that you'd like me to answer now?
There was some discussion in the chat about why is the brain better at this? Because the brain doesn't completely overheat and melt. But various comments were, let's ask Steve further that.
Yes, Steve has a good line in talking about the efficiency of computation. The best that we can do at the moment, and you'll see it in a later slide, is somewhere around 3 to 5 teraops per watt. The brain is something like 10,000 times more efficient than that. Part of the answer is that the brain is run on very slow chemistry type designs, whereas we're running on electricity. Electricity is a fundamentally more expensive way of doing the computations than chemistry. The other part of the answer is that as engineers, we like to have all the margin of getting the right answer in all the time. So we waste quite a bit of power just to make sure that we got a precise, repeatable answer that was the same all the time. So we could get a factor of 10 to 100 times closer to the brain by accepting its levels of inaccuracy. Getting the wrong answer is a great way to reduce power. Who knows if getting the wrong answer inside the brain is responsible for flashes of genius.
There's also some questions saying, are we reaching the limits of silicon? And would we be looking at optical transistors or quantum transistors?
Well, quantum transistors are far bigger, but contain much more fun, as it were. Instead of having binary states, you have quantum states. And depending on how you're able to read them out, a single qubit in a quantum computer can represent thousands of states, which you would have needed tens of thousands of transistors to represent. So far, quantum computers are only good at solving problems that quantum computers are good at solving. So, but work proceeds apace, and who knows? I mean, other places you can look for efficiency, even if you want to use electrical systems, are moving our computation away from digital to analog zones. So instead of multiplying digital bits together, current sum in resistors so that you get the effect of a multiply, and so on. Computing optically is a real problem because all your I/O has to be digital electronics, and converting between electronics and optics is a complete pain in the arse, slow and power expensive. We might see optics used for, quotes, long distance computation in the nearish future, but it might only be specialized jobs for it. Maurice Wilkes had a nice quote about optics. Beams of light don't interfere with each other very well. So since computation is all about things affecting each other, it's better to work in a media like electricity, where that interference is easy and obvious to control, whereas it's very hard to make beams of light affect each other. It's possible. There are people working on types of optical processing, but it's probably further off than anything else I shall mention. Any more questions, or shall I go on? I
think, well, yeah, do you want to continue for now, and we'll see what else we have by the end. Thank you.
So this is 48 years of microprocessor trend data. A multiple chart. The number of transistors has gone up very satisfactorily, one might say, if number of transistors were all. Single thread performance, as we've seen, has somewhat leveled off. It hit a limit and hasn't really gone up. Frequency seems to have hit a limit and bounced off and then started going down again. So we got to processors with 4 or 5 gigahertz. They got too hot. We seem to be better off with processors that are 3 to 4 gigahertz. They're much more useful. So frequency, we're already retreating from the bleeding edge. Power, typical power is still going up as the number of logical cores keeps going up. The typical power is just edging up, and every excuse we can find for burning more power, the industry takes. So that's sort of disappointing for anybody who thinks there are good things coming. There are good things coming, but not where they've traditionally been. So what's going to happen? We can use more transistors than we do today. That's taken as read. So today, where are we? We've got leading designs that are superscalar out-of-order processors. They do 6 to 8 operations peak per cycle. Intel started doing this earlier than anybody else. So they've had Haswell, Broadwell, Skylake, Kaby Lake, Coffee Lake, Ice Lake, Rocket Lake, Tiger Lake, etc. And these have been iterations of the fundamental Haswell type architecture. Intel have stretched it gradually. They've added a few more operations here and there. AMD really only became competitive with Zen and Zen 2 and now Zen 3. And they are in a similar area, but more power efficient than the Intel designs. Apple started making their own cores with Twister, went through Hurricane, Monsoon, Vortex, and now Firestorm, which is the processor underneath the A14 and the M1. Firestorm is very aggressive. It's 8 operations peak per cycle and then some. It's the widest of the architectures. Samsung were unfortunate. They developed a processor called Meerkat, M3, M4 with M5 and M6 in research, and they've now discontinued it. It is obvious that their performance was lagging, particularly Apple's, but even Intel's. They were burning too much power. Making these processors power efficient is really, quotes, where it's at, unquotes, because superscalar out of order isn't particularly energy efficient, but it can be made to run quite quickly. It runs quite quickly because it makes local decisions. So if you make a microprocessor simply, a simple in order pipeline, then things at the back of the pipeline have to store the front of the pipeline. Superscalar out of order, you have some stuff at the front that tears things apart and renames registers and allocates resources and stuff like that. And that stuff's not particularly dependent on the stuff at the back of the machine, which takes the torn apart parts and executes them out of order. And you find that you can make local decisions throughout the design. There aren't signals going everywhere, and you tend to be able to make them run quite quickly. This is sort of the opposite of what people expect. They sort of, and it was true in the late stages of early RISC designs, they thought that making designs like DEX Alpha and Titan processors, a simple microarchitecture would run fast. So there was a sort of war between complex microarchitectures and simple microarchitectures, but the simple microarchitectures would be rockets and go really fast, and the complex ones would go really slowly. But it happened that it worked out the other way around. Complex microarchitectures could be made to run far faster than simple in order ones when you account for stall behavior. Trying to make the things go fast and execute a lot of operations per cycle is very tricky, because fundamentally in there you have to get the results out of each operation and pass those results back to every other operation in the machine. So the number of operations you present goes back into bypass networks and such like that spread through the machine. And it's very hard because there's an n squared growth in doing that. So as you 6 to 8 only gives you at most 30% performance gain, but 6 to 8 gives you a 36 to 64 jump in your bypass network costs. So nearly doubles your bypass network costs for a third performance gain. Apple seemed to have managed this better than anybody else. Firestorm runs 8 operations peak per cycle, and in some cases seems to be able to sneak more in. Firestorm's also got more load stores per cycle than any but the specialist processors. So things like Firepath can outperform Firestorm's load store capability, but for a superscalar out of order processor, Firestorm is quite impressive in what it can do. So it's interesting to look at these things. So this is back in 14 nanometers. Intel at the time had the Broadwell design. In 14 nanometers on Intel's process, Broadwell uses 11.6 square millimeters of silicon. So it's quite big. Apple with Hurricane used less than half that area and were getting quite close. They were better than half the performance of a Broadwell, but we're losing quite badly at this stage. At the time, Qualcomm did make their own processors. Nowadays, they badge engineer ARM's designs. So the Qualcomm Cryo of the day was quite a good processor for the area it used. And the Samsung M1, the first of the Meerkat range, was also fairly decent. Both of those outperformed the Cortex A72 of the era, though obviously Hurricane outperformed all of them. Well, not necessarily, obviously. And on here, we've got two in-order cores, Cortex A53 and the Apple Zephyr core. Zephyr's significantly faster than the A53. In fact, I think at times it's faster than the A72. So, in 14 nanometer, Intel was a clear victor, but did spend a lot of silicon to get there. Here they are in 10. Intel have moved forward to Skylake. The transistors got smaller. Skylake was the first thing that Intel put onto any sort of 10 nanometer process. This is the one that was only released in China in certain laptops because it was distinctly uncompetitive, but the area comparison is really honest. Apple had got to Monsoon. They were about 75% of a Skylake in performance terms, but they're something like a third the area. Meerkat was now larger, this is M3 I think it is, than Monsoon, and performs worse than Monsoon and burns more power. Cortex A75 did a pretty reasonable job, better performer than A72 and A73, and the little Apple core of the time, Mistral, completely destroys A55 and A53, and can mostly outperform A73. So for equal silicon area, Apple can already put down something that's better than Skylake in 10 nanometers. And the situation, I don't have pictures of them, is repeated for Firestorm. So we've seen a little there about big and little cores. So big and little, and now I'll call it dynamic, tries to attack power inefficiency of superscalar out of order by providing both power efficient little cores and power burning big cores. So for example, A76 with A55. And that paradigm has caught on everywhere except at Intel. So with Apple, Monsoon and Mistral, Lightning, Firestorm, Lightning and Thunder, Firestorm and Ice Storm are big and little cores. Apple's little cores, I think I have to call them middle size. They're far better than anybody else's little cores. Little cores are quite nice because extra transistors are quite cheap, and little cores are quite small. So adding little cores is fairly cheap. You can use the little cores simultaneously with the big cores and turn all 8 or whatever number you have on. It doesn't increase peak scalar. You have to have your big core up for that. And of course, originally when ARM designed big little, you had to have matched big and little cores, one of each. So quite a lot of people are still in the 4 big, 4 little architectural world. But dynamic shows that you can have arbitrary mixers. So there have been people with 2 big, 4 little, or 6 little, 2 big, 2 middle, and 4 little. That was MediaTek. Nowadays, Qualcomm go for 1 prime core, a big core with all the numbers turned up, 3 big cores with all the numbers turned down, and 4 little cores. All trying to just edge the equations between power efficiency, peak performance, how difficult it is to rewrite their operating system scheduler to get the right core to do the right things when somebody's running a benchmark, that sort of thing. So Big Little has been quite a good thing. It's applied basically everywhere except Intel. Intel just put down really big cores and try and turn them off when they aren't using them. This does mean that practically everything made by Intel overheats too quickly. They can't back off a big core enough. So a cheap prediction is that Intel will start doing mixed core sizes. In particular, Intel have a little core range, Goldmont and so on. I've forgotten what its generic name is. Atom, that's what its generic name is. So to go alongside Core, Intel have Atom things. So Intel will build something with an Atom core matching a big core type machine, just because the power efficiency matters. So there are also unconventional designs, things that aren't superscalar out of order or superscalar in order designs. So there's a lot of people using VLIW. So NVIDIA made ARM cores called Denver and Carmel, very high operation count VLIWs with hardware JIT converter from the ARM instruction set. VLIW is used in a lot of signal processing. Qualcomm have Hexagon, Broadcom have Firepath, another processor you won't have heard of called VASIP. Sabre have X and XC, Silica have BBE, TI, Velocity. They all use VLIW for signal processing, often with a few novel microarchitecture features. Mill Computing are preparing a VLIW-like machine. I call it like because it's more like the hybrid offspring of a VLIW machine and a stack machine. But again, it's very high operation count, 30 operations per cycle. I showed you Firepath doing 4 operations named by the processor per cycle that were broken up into smaller operations. So Mill Computing have a 30 operation per cycle machine. Just like the superscalar out of orders, VLIW has trouble with bypass networks. But VLIW does tend to be extremely power efficient. Most of these processors can execute at efficiencies that the processors we've been mentioning before have difficulty imagining, which is why you find them doing heavy lifting like signal processing, where a conventional processor just can't do it. The other thing that's happening is what we compute is also changing. So, we started off with general purpose computing. We started making specialty signal processors and then graphics processors. And now we have deep learning engines, variously called IPUs, DNNs, knowledge processors, all sorts of names for them at the moment. These things have hallmarks, much smaller processing than a C int 8 or 16 or smaller even. Processing can be done with integers without floating point. And these things are often massively parallel, and it's parallelism that can be used. This is parallelism that is not subject to Amdahl's law. So, for example, in doing convolutional neural networks, the Google TPU has 64,000 8-bit integer multipliers. So it is doing 64,000 multiplies per cycle. So on top of this, if you've got multiple of them, multiple TPUs, IPUs, DNNs, whatever their name is today, the problems that they're solving tend to be very amenable to parallel architectures. Again, without too much loss of Amdahl's law in synchronizing things, if you're multiplying together 2 ginormous matrices, you can, with very little synchronization overhead, do the work across parallel machines. And these are the things that can be highly efficient. 3 to 5 teraops per watt, where conventional microprocessors have difficulty accessing the 3 to 5 gigaops per watt. And we've mentioned Steve, so here's another cue. Spiking neural networks, particularly if you build them with analog technology or nearly analog technology, can be more efficient again. If you can replace your multipliers with current sums or capacitor charging or things like that, then you can really become a lot more efficient, though still with the disadvantage of being electrical rather than chemical compared with the brain. So Steve's Spinnaker simulates spiking neural networks with a digital processor. So he has the algorithmic efficiency of spiking neural networks, but running on the digital inefficiency of doing it digitally. But at least he gets repeatable answers. So we see that chips have got stupidly complicated. So this is an NVIDIA chip, 9 billion transistors in 350 square millimeters, and it is covered with processors. Steve and I looked at each other when we learned that ARM had sold 10 billion chips based on ARM cores. We no longer care, given that they're knocking out about 30 billion a quarter. So in 2008, it was 10 billion chips. Now, the total is in the hundreds of billions of chips. And a lot of it is that you can have a lot of ARM cores. ARM no longer bother counting the number of ARM cores on people's chips. So NVIDIA into this have crammed, well, starting on the right-hand side, image signal processor that can deal with 1.5 gigapixels, 8 of their kernel VLIW ARM64 engines, 10 wide, as it were, superscalar VLIW entries. On the left-hand side, they've put a Volta series GPU into it, which can handle 32-bit floating point, 16-bit floating point, 8-bit integers. And there's 512 of those crammed in there. So you've got 1.3 teraflops when executing NVIDIA's CUDA programming languages for parallel programming on GPUs, or if you're doing work on tensors, matrix multiply, that sort of thing, they've got 20 teraops crammed into that bit of the machine. And then they've got a programmable video accelerator with 1.6 TOPS in it, where they do image processing, optical flow. The main supervising video processor for codecs. So this thing can encode and decode video streams. And then they have another digital learning accelerator that, because the hexagon core, VLIW core can also do that. So we've got another 5 teraflops of floating point or 10 TOPS of 8-bit integer work. And they've got some high-speed coherent serial interfaces, 109 gigabits per second. Such fun. They interface to 256-bit wide LPDDR4 memory at 137 gigabytes per second on the bottom. So yeah, you can have a lot of fun with a piece of silicon. It's just very expensive to make it. We've been kicking Intel for a while. Doing this presentation. It's all good, clean fun. Here's Intel's 2019 investor roadmap, where they said they'd have 7 by 2021. They don't have it, but relentless Innovation does continue. They will get better. But you'll see just how long they've had to suffer being on 14. From 2014 through to 2018, it was their only available process, and they are still producing chips on 14. They've even backported the Willow Cove core onto 14 to produce Tiger Lake, I think. So 14 is the only process they've got that can get really fast and hence really hot. In 10, they've mainly targeted their 10 stuff at laptops. So that's been a lot of their market, but they're finally bringing 10 nanometer into the most lucrative bit of their market, which is obviously server CPUs. So they've now released on the superfin process in 2021 the first server Xeon, the 2 processor socket Ice Lake. When they presented this, they said they'd have 7 in 2021. Probably won't be till the end of 2022. I wish them the best of luck. So we already went from planar to FinFET on transistors. As we shrink, FinFETs stop working. Shame. So we're going to have new transistors soon. 3 or 2 will be new transistors. So either nanowires, where we build some wires and wrap the gates around them, or nano sheets, where we build some sheets and wrap the gates around them. Samsung prefer nano sheets. TSMC prefer nanowires. Beyond that, it seems likely that we'll have to design a transistor that is 2 transistors at once in order to squish things together even more, instead of designing a transistor in isolation, even designing it to be vertical out of the silicon to save planar area. We'd like to design things where the complementary FET that we design in is built in one step, so that you build both an N-type FET and P-type FET at the same time, integrated together, in order to shove the density up. So that's a possible future. Whatever's going to happen, we know it's going to use more power. And we know that we're going to have more expensive transistors. So these 2 slides look at what's going to happen with those 2 problems. It's really no longer cost effective to build a system on chip in the most advanced process, since the advanced transistors cost so much more. So what's been happening for the last year or 2 very visibly with AMD and gradually dragging Intel into the world, who've been researching this for ages but not putting it into any products, is to use advanced packaging techniques, put only some of the system onto the most advanced process and the rest onto something cheaper. AMD and most of the industry call this chiplets. Intel called it Foveros, and Intel tend to think of it in terms of packing things together in smartphones. So AMD's Zen range is made with chiplets. So they have computer cores and I/O cores, and they're on different technologies. So Zen 3, the compute cores are on 7 and the I/O cores are on 14. And this is quite fun because it means AMD have only made 2 things, a 14 nanometer I/O core, that's the big bar in the middle on the green picture on the right, and a 5nm compute core, and they've designed their system such they can put between 1 and 8 compute cores onto the I/O core. So by packaging alone, not having to do more tape outs and chip qualification and all that sort of thing, they can build things from one pair of things, the I/O core and the compute core, together to 8 compute cores, 8 compute core chips. The current compute core chip contains 8 CPUs, so they can effectively scale from 8 CPUs to 64 CPUs easily. So that's how AMD managed to bring out the vast range of things that they now supply. You get all the Zen systems, the Epics, and the Threadrippers out of the same design work. Threadripper needs a better I/O chip, but the same compute core. Intel planned, using Foveros, to put some big cores and little cores together. That's what they told their investment group in 2019. They've yet to do that. So we've got all that heat. At present, we cool the external package. So lots of people are working on how to cool it directly, especially if we're going to put things closer together, 2D, 2.5D, don't know how to cool 3D. So this is one perspective solution, a multi-jet cooler. So you have tiny holes to shoot the liquid out and a big vent to take the liquid back. So you spray cold liquid, not conducting liquid obviously, onto your hot chip and take the now heated up liquid away. So it may be that, particularly for servers, we need to do this. The most power hungry of AMD and Intel ranges are now hitting 250, 300 watts in use. So they're right at the limits of where air cooling can possibly work. And you probably need to at least have a water-cooled system, if not this direct cooling system, just to make it reasonable, or else the fans will be like the opening to Apocalypse Now. And the last thing we can do is wafer scale integration. So you thought the numbers before were quite big. This is Cerebras's wafer scale integrated AI system. 46,225 square millimeters silicon, 1.2 trillion transistors, 400,000 AI optimized cores, 18 gigabytes of on-chip memory, 9 petabytes per second of memory bandwidth, 100 petabits per second of fabric bandwidth. And they only built it in the 16 nanometer process because they're a startup and can't afford anything more advanced. The next generation will clearly be built on something like TSMC 7 or 5, now that they can have proved that their stuff works. So that really is a large chip that he's holding, where I was holding a tiny little dot of one microprocessor, he's got 400,000. So that sort of thing can be made to work. On the downside, that particular machine does use 25 kilowatts. So that single chip that he's holding, that single wafer scale integrated design, has to be mounted on a very special liquid cooled system to take the 25 kilowatts away. So that's it. We are now open for questions for about 10 minutes.
Well, thank you very much, Sophie. I'm aware you've already done longer than you were intending, so thank you for that.
Yeah. Well, it's the break and starting late. We didn't.
Well,
cleanly.
Throw a couple of the questions I picked out. Someone asked what programming languages you would recommend for the kind of forthcoming parallelism that's needed, and what's good for building that sort of software.
No programming languages are good at the moment. Everybody is writing inadequate programming languages with inadequate operating systems. It's a big problem. The hardware is designed with programming languages that have explicit parallelism in them. So something like Verilog or VHDL is all about expressing your parallelism at a programmatic level and making sure that it works. So people who design hardware with explicit parallelism have an entire set of tool chains and systems to make that work. People who program them don't, in a nutshell. You have some things that are clearly pointing some sort of little way. CUDA itself is a fairly successful compute language for GPUs. OpenCL is a less successful compute language for GPUs. So those are good things to sort of think about a bit, but they're just too small to write anything real in them. At the moment, everybody writes things at a higher abstraction level and relies on somebody else to have done the donkey work in providing libraries that do the work. So, you know, if you look at machine learning, everybody talks about TensorFlow as if it's magic, but TensorFlow is just a thing written in a shoddy language, calling out to libraries that other people provide for doing matrix multiplication, convolutions, etc. And it's those libraries that have the heck optimized out of them.
When you showed earlier the Firepath kind of assembler code, does anyone actually really use that, or is it all directly, or is it just spat out by compilers? Does anyone really write the assembler code anymore?
We have the odd Tim Dobson and Mark Taunton around who write Firepath assembly code. It's all the 90-10 rule. As you're aware, 90% of your time is going to be spent in 10% of your code. So you only have to speed up that 10%. You can get the compiler to help because you can represent the complicated objects with what C calls intrinsics. C in compiler language calls intrinsics, so you can use the compiler to do all the data flow management and allocation of things and moving things in and out of memory with the intrinsic that does a mul2w or whatever wacky. I mean, Firepath has things for Gower field execution. So, you know, Gower field instruction, put that in the middle of your algorithm and let's see the compiler sort out the rest. And that's how the non-Tim Dobsons and non-Mark Tauntons write code for Firepath.
Still some of the old names still around, basically.
Tim Dobson has worked for me for a distressing number of years.
Someone else said that about the original ARM had a very elegant kind of instruction set. It's all very regular and neat. Is that still the case, or is it now a case of just if it gets the job done, just throw the kitchen sink at it and it?
So everybody misunderstands what RISC processors are about. So RISC stands for Reduced Instruction Set Computers. But they can have extremely large instruction sets. I mean, ARM's instruction set is arguably larger than the 6502's instruction set, where the 6502 was a complex instruction set computer. The reduction is in the microarchitecture that's required. So it's a reduced instruction set complexity computer, not a reduced instruction set computer. So within the framework of the load store microarchitecture that RISCs all have, you can have arbitrarily complicated instructions. if we made a RISC version of a Firepath, then you could still have a Galois field instruction, because that's a data processing task. And it would still be a RISC, because RISC applies to how complex it is to execute the instructions. So it would still be a load store microarchitecture. It would just have a Galois field unit bolted into its processing units. Yeah.
Right. What were the other questions I saw that came up? Oh, going way back in time, someone asked a fun question. What was your favorite of the Acorn computers? Stretching it.
A lot of them. You can't compare your children, can you? It's like that is like asking what's your favorite child. At any given time, the one I was working on was my favorite.
That's probably a good answer for someone who's trying to advance the field, really. It's going
to... It must be understood that although I haven't worked on Acorn computers for quite some time, I still have a lot of fun.
Yeah. Well, that kind of leads to one question that Steve Scott asked. He said, had you ever thought what would have happened if you hadn't started out with that cow feeder, developing that, and then leading on to ARM? Where would things have gone?
I mean, essentially developing that cow feeder got me the ability to say to Herman that I could design his pocketbook, which got Herman to eventually ask me about my own home computer and the designs I had for an MK14-like one, which became the Acorn System one, etc. Yeah. I look at my career where I've never applied for a job and done a job interview in my life as a series of fortunate accidents.
If the ARM hadn't been developed, how do you think the computing world would be different from that?
It wouldn't be very different at all.
What would architecture would have come along instead, do you think? MIPS, maybe?
Somebody else would have made something similar. There was tremendous pressure within the industry at the time where Berkeley RISC One, MIPS from Stanford, ARM, IBM 801. There were a dozen more internal designs from various companies going on. Some of those arguably would have been more successful if ARM hadn't come along and would have filled its niche. I don't know which one from this perspective, because ARM was successful.
Well, there's more and more questions coming through here. I can't keep up with this.
Well, I'm going to make it simple for you. You've got 5 minutes maximum.
How many 5 minutes maximum? That's tricky then to pick a question out.
Yeah.
Try and unmute people so that people can at least show their appreciation. I think the only way I can do this though is by muting everyone and then letting them unmute. So you're going to get muted as well, Sophie. So hold on a second. Right, people should be able to unmute themselves now. So everyone just at least nothing else. Maybe a round of applause while we've got the chance.
I've got a question. I've got a question for Sophie.
Right. Thank you, everyone. I know David said he had a particularly question that was difficult to ask in the chat. So if he wants to go for
Yes,
it.
there wasn't room. I couldn't get enough room in the chat window to ask the question. Now, it's to Sophie. Around about 2005, you gave a talk at a retro computer exhibition at Bletchley Park. Now, in the question session, I asked, this was long before SoftBank bought ARM. I asked the question whether, what was the chance that ARM could be bought out by some company? And you said there was no chance at all. It wouldn't happen because you gave reasons, and it was something along the lines that any company that bought it, the value of the ARM would fall because it would not be able to be an independent supplier of designs, hardware, computer core designs for around the world. So you said it wouldn't happen, but it has happened. And I mean, we sort of went along with SoftBank, I suppose. We explained it away. We said SoftBank wasn't a chip designer or a chip fabricator. But now NVIDIA seem to have got it. What are your comments on that?
So my argument before was nobody could buy ARM because if you were a member of the semiconductor microprocessor community, then you would destroy the value as you bought it. SoftBank was a very strange situation in that it had no real interest in what it was buying and didn't participate in the community. It was a pure investment ploy by a company that needed to get new investments in order to keep growing its valuation. This has subsequently failed, and SoftBank needs to sell ARM. Now the only buyers are possible companies that are a member of the microprocessor field. The UK government has announced today that it is going to investigate and may decree that ARM cannot be sold to NVIDIA. So who knows if NVIDIA will be allowed to purchase ARM.
Oh, that's some hope there, some hope.
I don't know if there's any hope at all. SoftBank still has to sell ARM. SoftBank's other investments haven't gone well, and Mr. Son still wants to grow the valuation of the company. So he needs to divest and start out again. Which is very tricky.
I'm aware we're getting on in time.
Yep.
So I asked one last quick question that was just a fun one that was right near the early bit of the chat. Someone said the original ARM evaluation system had a Amdahl command. Kind of why? And was it just for fun to prove a point?
Well, it was actually BBC Basic that had
the BBC Basic, sorry,
keyword in it, and that was just for fun because we were playing with Mandelbrot sets. You would have seen several demos come out of Acorn at the time with some sort of Mandelbrot in them. One of the ones I did was a Mandelbrot set mapped onto a reflecting sphere with the word Acorn spinning around in balls, the whole thing ray traced. So to do that sort of thing, it helped to have Mandelbrots go as fast as ARM could do them rather than as fast as a programming language could do them. So I implemented a Mandelbrot keyword, wrote the Mandelbrot fundamental algorithm in ARM machine code, and made it go fast. It didn't go as fast as, say, Stephen Streeter's Mandelbrot program, but I did get prettier answers.
Yes, we have had Stephen Streeter speak at ROUGOL before. Yes, very clever guy as well.
Yes. Well, I mean, in my career, I think most people are cleverer than I am. I just happen to have more fortunate accidents than most people.
I think you make your own accidents, don't you, in this case?
The harder I work, the luckier I get.
Yes. So unless anyone has any burning questions.
I actually have a question. You talked about the specialized cores that are present in modern CPU architecture and the impressive level of DLP, data parallelism. Do you think that in the future we are also going to see that those specialized core become like multi-core within the same architecture? The reason why I ask is because we are seeing the impressive growth of AI, for example. And so on a general computer, there might be multiple applications having needs for AI computational in concurrency.
I think I mentioned that when I was mentioning accelerators for machine learning. Machine learning is the better phrase. These are not artificially intelligent.
Yeah.
They are statistically trained weapons of mass destruction. So you can devise things that, the Google GPU is a systolic array of 64,000 multipliers, and then you can use multiple TPUs in parallel on the same matrix multiply. And you can do it the other way around as well. Instead of designing a big hammer like a TPU, which has got 64,000 multipliers in, you can design a small hammer like a Cerebras core or a Graph core, IPU core. They're much smaller cores that only do a bit of the work, and then you can use thousands of them to do a matrix multiply with and get back up to the 64,000 multiplies per cycle. So both ways work because the parallelism has been taken away from the programmers and been given to the hardware engineers. And the hardware engineers can attempt to provide an appropriate solution. Briefly, the advantages seem to be that if you design a big hammer like a TPU with 64,000 multiplies, you can make it really power efficient for that one job. If you design tens of thousands of IPUs or Cerebras cores to do the same task, then you have a chance of dismantling them and putting them into some other organization to do a different job, which is what GraphCore tries to do with its Poplar compiler and what Cerebras tries to do with its compiler, to use the cores in different ways. Jury's out yet as to which will be successful. All machine learning companies for the last 3 or 4 years have gone reasonably well. They've either been acquired by somebody or have massive backing from venture capitalists. But statistically, 9 out of 10 venture capital-backed companies fail. So there will be a shakeout at some stage. A lot of the acquisitions, particularly some of those made by Intel, have already been effectively wound up inside the company. So who can tell? It's too early for that. That's why it's only a sort of, the future could look like this in my slides.
Thank you very much.
So I think that has to be the end, and I have to say goodbye and go to bed.
That's great. Thank you very much, Sophie. You've stayed longer than you intended, so
I have.
Really fascinating. Thank you.
Thank you.
Thank you.
I shall press the leave button.
All right, maybe we'll see you again in another 10 years. Thank you.
10 or 11.
Right. Thank you again. Good night.
Just to note for everybody that in a week it will be the whatever it is, the 26th of April, which is the anniversary of the first ARM working.
Great anniversary.
Anyway,
Good night.
bye.